Usually when we talk about digital design on this deep dive, there's this underlying assumption of just absolute perfect precision.
Right.
You sit at your computer, you dial in the exact hexadecimal code for midnight blue, you align your typography down to like the fraction of a pixel, and the screen just complies without questions.
That's a totally frictionless environment.
Exactly. But the moment you hit print, you step out of that pristine digital utopia and into the real physical gauntlet of manufacturing. Suddenly, that perfect digital file is subjected to massive machinery, gallons of liquid chemicals, immense mechanical pressure, and razor-sharp steel. So today, our mission is to decode the physical reality of design. We are taking a massive journey through the exact physics, chemistry, and mechanics of printing and finishing.
It really is a profound transition, you know? Designing on a screen is honestly only half the battle. Knowing how ink actually physically interacts with paper fibers and what happens to that paper under extreme duress is what separates a theoretical design from a functional object. I mean, the physical constraints of manufacturing dictate entirely how the final audience is going to interact with the piece.
Yeah, 100%. So if you are prepping for a major production run or trying to reverse engineer how a specific physical effect was achieved, or even just looking to understand the complex supply chain behind the objects you hold every day, you are in the right place. And before we get into heavy machinery, I just want to remind you to subscribe to the channel. We do deep dives into complex professional topics like this regularly, breaking down the mechanics so you can apply them directly to your work.
Yeah.
And if you want to follow along with the foundational industry standards we're discussing today, you can grab a physical copy of the definitive manual on this. It's called Graphic Design Reference plus Specification, specifically Chapter 13. Just scan the QR code on your screen or use the link in the description. All right, so let's start at the absolute foundation of modern high-volume manufacturing, the offset press.
Right, the offset press. If you look at a printed magazine, a high-end catalog, or like a corporate brochure today, you are almost certainly looking at offset lithography. It is the undisputed workhorse of the global printing industry.
Yeah.
But what's fascinating is that beneath the massive steel frames and computerized control panels, the entire process relies on a very simple, very old chemical principle.
Yep.
Oil and water repel each other.
It's basically kindergarten science scaled up to an industrial level, right?
Exactly.
Because the printing plates themselves, they aren't carved or stamped with raised letters. They are completely flat aluminum sheets. The trick is entirely chemical. The areas of the plate that carry the image, so the text and the photographs, they're treated to be lipophilic.
Right, meaning they attract oil-based ink and repel water.
Exactly. And then the non-printing areas, the blank spaces, are hydrophilic. They attract water and repel the ink.
Precisely. And to understand how that chemical separation actually translates into a crisp image on paper, we have to look at the mechanical choreography inside the press. It relies on 3 specific, highly calibrated rotating cylinders.
Okay, let's unpack this.
So first you have the plate cylinder, which holds that chemically treated flat aluminum plate. As it rotates, it first makes contact with a series of dampening rollers.
Okay.
And these rollers apply a micro-thin, highly controlled layer of water-based solution over the entire plate. Because of the chemistry we just talked about, the water only adheres to the blank, non-image areas.
So the plate is essentially acting as an invisible chemical stencil. The image areas remain perfectly dry.
Right. And in the very next fraction of a second, the plate cylinder rotates past the inking rollers. And these are coated in a thick, highly viscous, oil-based ink.
Got it.
Because the blank areas are currently wet with a dampening solution, they actively repel the oil. The ink only physically bonds to the dry, receptive image areas.
See, if the plate is fully inked with the image, my instinct would be to just roll that metal plate directly onto the paper. Yeah. But that's not what happens, is it?
No, it's not.
That's where the offset part of offset lithography comes in.
Yeah.
The middle plate transfers the ink onto a second cylinder, the blanket cylinder, and that one is wrapped in a thick compressible layer of rubber.
Yeah, and that rubber blanket is the great equalizer of the printing world. I mean, think about the microscopic topography of paper.
It's pretty rough, right?
Exactly. Even a sheet of high-gloss coated paper isn't perfectly flat. Under a microscope, it's this chaotic, interwoven landscape of wood fibers, full of microscopic peaks and valleys. If you pressed a hard, unyielding aluminum plate directly against that landscape, the ink would only hit the peaks. You'd get a broken, speckled, uneven image.
So the rubber blanket acts as like a highly specialized shock absorber.
Exactly. The rubber is compliant. It accepts the pristine wet ink image from the metal plate, and then as the paper is fed between that blanket cylinder and a third cylinder, the impression cylinder.
Which provides the backing pressure, right?
Right, immense backing pressure.
Yeah.
The rubber physically squishes and conforms to every microscopic valley in the paper's surface. It forces the ink down into the texture of the substrate, ensuring a perfectly continuous, sharp image. And that works regardless of whether you're printing on smooth-coated stock or a highly textured linen paper.
That's wild. So the mechanics of those 3 cylinders dictate the quality. But the way the paper is actually fed into that system completely changes the logistics and the economics of the job.
Yeah.
You essentially have 2 major operational frameworks here, web offset and sheet fed offset.
Yeah, and that choice dictates the speed, the scale, and the ultimate precision of your entire production run. Let's look at web offset first. In industrial printing, a web refers to a continuous, unbroken ribbon of paper.
Okay.
These machines do not use pre-cut sheets. They are fed from absolutely massive, multi-ton rolls of paper that unwind into the machine under extreme tension.
The scale of web printing is just staggering. We're talking about paper traveling through these cylinders at thousands of feet per minute. Because the paper is a continuous roll moving at that velocity, the ink simply doesn't have the time to dry through normal ambient evaporation, does it?
It really doesn't. And that necessitates entirely different hardware integrated into the press. Web presses, particularly those printing high volumes of color, are equipped with massive inline heating chambers.
Like actual ovens.
Literally ovens. The continuous web of paper flies through a high-temperature oven that flash vaporizes the solvents in the ink in a fraction of a second. Immediately after the oven, the paper passes over chilled rollers to instantly freeze the remaining resins and pigments into a solid state.
Wow.
Yeah, so the ink doesn't smear when the paper is subsequently folded or rolled.
And the paper is only sliced into individual pages or signatures after it has run that entire gauntlet of printing, baking, and chilling.
Exactly.
Now, within the web category, you have different tiers of machinery based on the width of that paper roll. You have smaller form webs, running rolls, maybe 9 inches wide, which are highly efficient for producing millions of utility bills or direct mail letters. But then you have the full web presses.
Yeah, the full web presses are the leviathans of the industry. These utilize rolls of paper spanning 35 to 40 inches wide. To conceptualize that output, a single full web press can print an entire 16-page signature.
And a signature is a grouping of pages that will eventually be folded and bound into a publication, right?
Right, so it prints that entire 16-page signature on a massive section of the web, roughly 23 by 35 inches, in a single instantaneous pass.
That's insane. These are the machines engineered to output the daily metropolitan newspapers, the massive national retail catalogs, the weekly news magazines. The sheer brute force is incredible. The paper roll feeds into one end, and completely finished, folded, glued magazines can literally shoot out the other end.
It's a marvel of engineering.
But that extreme velocity comes with a trade-off in absolute precision, which brings us to the alternative framework, sheet-fed offset.
Right, so if we connect this to the bigger picture, sheet-fed operates on a much more controlled, granular level. Instead of a continuous high-tension web, the press uses complex pneumatic systems, essentially a series of highly calibrated vacuum suction cups.
Okay, I love that visual.
Yeah, they pick up individual pre-cut sheets of paper from a stack, feed them through the cylinders, and neatly stack them at the delivery end.
Because you aren't fighting the terrifying mechanical tension and physical stretching of a continuous roll, I assume the registration, the precise alignment of the cyan, magenta, yellow, and black ink dots can be dialed in much tighter on a sheet-fed press.
Dramatically tighter. Sheet-fed provides superior image clarity, sharper halftone dots, and incredibly rich color fidelity. It is the methodology you choose when absolute perfection overrides pure speed. High-end museum art books, luxury automotive brochures, fine art reproductions, these absolutely demand sheet-fed offset.
And the physical footprint of these sheet-fed presses varies wildly, doesn't it? You can have a small 2-color sheet-fed press handling paper under 18 inches wide, which is perfect for high-quality corporate letterhead or invitations.
Yeah.
But you also have massive sheet-fed presses that can accommodate single sheets up to 55 by 78 inches.
Yeah, and that massive real estate is highly strategic. It allows production managers to utilize ganging. Yeah. Say you need to print 50,000 standard-size promotional postcards. You don't run 50,000 small pieces of paper through the press. You meticulously lay out dozens of those postcard designs onto a single 55 by 78 inch sheet. You print a few thousand of those massive sheets and then trim them down later. It drastically reduces the number of impressions and the overall time on press.
So offset, whether the massive volume of web or the precise control of sheet fed, requires the creation of physical aluminum plates. It requires an operator to mount those plates, ink the rollers, balance the water-to-ink ratio, and run hundreds of sheets of paper through the machine just to calibrate the colors before the actual production run even begins.
It's a very involved process.
That entire setup phase, the make-ready, represents a massive upfront sunk cost in time and materials.
Which is exactly why offset is economically unviable for very small quantities. If you only need, say, 100 copies of a beautifully designed corporate report paying for the aluminum plates, and the hour of press time just to calibrate the machine would result in an astronomical cost per unit. The make-ready cost totally eclipses the actual printing cost.
Right, which introduces the great disruptor of the last few decades. Digital printing, often referred to as on-demand printing. Digital fundamentally alters the physical process by completely eliminating the need for plates and the entire mechanical make-ready phase. The file goes straight from the computer to the machine. It is the perfect economic solution for short-run jobs, generally anything under 1,000 units.
It really is. But designers must understand that digital printing relies on a completely different chemical and physical mechanism to transfer color. Offset uses a viscous liquid ink that is physically pushed down into the porous fibers of the paper. It integrates into the substrate.
Okay.
Digital presses, conversely, utilize toner. Toner is not a liquid. It is essentially microscopic, electrostatically charged plastic powder.
Like plastic powder.
Yeah. The digital press uses static electricity to attract this plastic powder to the specific image areas on the paper. And then the paper passes through a fuser, a set of extremely hot rollers. The heat literally melts the plastic powder, fusing it onto the surface of the paper. The color isn't absorbed, it sits squarely on top of the sheet like a microscopic layer of colored plastic wrap.
Wow, okay. And that structural difference creates a significant vulnerability that production teams must engineer around.
Absolutely.
Because the toner is a fused layer of plastic sitting on the surface, it is brittle. If you take a heavy piece of cover stock with dense, dark digital toner printed across it, and you attempt to fold it in half to create a brochure,
It shatters.
Exactly. The plastic layer cracks violently along the stress line of the fold, exposing the raw white paper underneath. It looks jagged and incredibly unprofessional. You don't get that same severe cracking with offset ink because the liquid pigment has permeated and integrated with the flexible paper fibers.
Precisely. Designing for digital requires an awareness of these physical boundaries. You try to avoid designing heavy, solid color blocks that cross directly over fold lines. Furthermore, while the technology is constantly advancing, digital presses generally have stricter limitations on physical dimensions.
Right, they often max out around 11 by 17 inches or slightly larger.
Yeah. And they can struggle to feed exceptionally thick or heavily textured paper stocks that a sheet-fed offset press would handle easily.
While offset and digital clearly dominate standard commercial manufacturing, they aren't the only tools available. Sometimes a project demands a tactile sensation, an antique aesthetic, or a specific physical functionality that standard cylinders and lasers simply cannot provide. We have to look at the specialty presses.
Oh, this is my favorite part.
Let's start with the absolute historical foundation of the craft, letterpress.
Letterpress is relief printing in its purest form. It is the methodology pioneered by Gutenberg. Instead of a flat aluminum plate using chemical separation, letterpress uses a surface with significant physical depth. The image and text are raised above the background.
Right.
Historically, this involved manually assembling individual lead letters. Today, it more commonly utilizes photopolymer plates, where the non-image areas have been chemically etched away, leaving the typography and graphics physically protruding.
These raised elements are locked tightly into a heavy metal frame, the chase, and mounted onto the press. The rollers apply ink strictly to the raised surfaces. But the magic of letterpress, the reason it survives and is actively sought out today, happens at the moment of impression. The paper isn't just lightly kissed by a rubber blanket, right?
Right, it is brought down and physically crushed against those raised metal or polymer surfaces.
That mechanical pressure creates a distinct physical indentation in the paper. It yields a soft, inked impression that bites deeply into the fibers. You can run your fingertips across a letterpress wedding invitation or a bespoke business card and feel the topography of the typography. It is an undeniably tactile sculptural experience.
It's beautiful, but because it requires specialized plate making, meticulous manual setup, and runs at a fraction of the speed of offset, it is highly labor-intensive and expensive. It is explicitly reserved for projects where that artisan, antique, handcrafted aesthetic is the primary objective. You know, fine art books, high-end announcements, premium packaging details.
Right. Now, if letterpress relies on ink sitting on the raised portions of a plate, we have two other major processes that operate on the exact inverse principle: gravure and engraving.
Yes.
In these processes, the image is physically etched or carved into the surface of the metal plate, creating recessed wells or grooves. Let's examine gravure first, because it operates at a scale that dwarfs almost everything else in the industry.
It really does. Gravure uses massive, solid metal cylinders, often steel-coated in copper, where the image is translated into millions of microscopic recessed cups etched into the surface of the cylinder.
Microscopic cups.
Got it. The cylinder rotates through a highly fluid bath of ink, flooding the entire surface. Then, a perfectly calibrated steel blade, known as the doctor blade, forcefully scrapes the exterior surface of the cylinder completely clean.
So the only ink remaining is trapped down inside those microscopic etched cups.
Exactly. When the continuous web of paper is pressed against that cylinder, the capillary action of the paper fibers physically acts like a sponge, drawing the fluid ink out of the recessed wells. The image quality is staggering. By varying the physical depth and size of the etched cups, gravure can lay down varying volumes of ink, producing incredibly smooth, continuous tone imagery with a richness that offset struggles to match.
However, physically etching massive steel and copper cylinders with microscopic precision requires a gargantuan initial capital investment. The plate-making costs are just astronomical.
They are.
Therefore, gravure is economically viable only when that initial cost can be amortized over an incredibly long production run. We are talking millions of impressions. It is the domain of ultra-high-volume consumer catalogs, flexible plastic packaging for food products, and, weirdly enough, the mass production of postage stamps.
It's true, gravure is about monumental scale, but its cousin, engraving, is about unparalleled prestige and security, operating on a much smaller, highly specialized level.
Okay, let's get into engraving.
Engraving also utilizes recessed grooves carrying ink, but instead of a massive cylinder on a high-speed web press, it utilizes a flat, relatively small, chemically etched metal plate. The ink fills the recessed lines, the surface is wiped clean, and the paper is introduced. But the physical interaction here is incredibly violent.
Violent, how so?
The paper is forced against the etched plate with tremendous localized pressure. We are talking tons of mechanical force. The paper is literally squeezed and molded down into the microscopic grooves of the metal plate, forcing the fibers to extract the heavy, viscous ink from the recesses.
Wow, that immense pressure has to fundamentally alter the structure of the paper.
It does. It creates a sharply defined, raised, tactile surface on the front of the sheet. The ink physically stands up off the paper. Conversely, on the back of the sheet, you will find a slight indentation, a bruised impression where the paper was forcefully driven into the plate.
It is the exact tactile sensation you feel when you run your fingernail over the lapel of a portrait on paper currency. That raised, incredibly fine, almost sharp texture is the hallmark of true engraving.
Exactly.
Because of the slow process and the size limitations, engraving plates generally max out around 4 by 9 inches. It is reserved for applications requiring absolute authority and permanence. Actual currency, stock certificates, and the highly formal corporate stationery of international banks or historic law firms. It physically communicates wealth and stability.
It absolutely does. But what if a designer desires that sophisticated, raised ink aesthetic for a client, perhaps a local boutique or an independent consultant, but lacks the substantial budget required for true engraving dies? The industry developed a clever chemical workaround called thermography.
Thermography looks like engraving, but it's fundamentally different, isn't it? It's essentially an optical illusion designed to simulate engraving. It's the faux luxury option.
That's a great way to put it.
The printer lays down the design using standard offset printing, but utilizing a specially formulated, very slow-drying ink. While that ink is still highly viscous and wet, the paper passes through a dusting unit that coats the entire sheet in a fine, clear, resinous powder.
Right, and the powder adheres strictly to the wet ink. The excess powder on the blank areas of the paper is vacuumed away. The sheet is then transported through a radiant heating tunnel. The intense heat melts the resin powder and the wet ink together, triggering a reaction that causes the mixture to swell and expand upward. As it cools a few seconds later, it cures into a hard, glossy, raised impression that physically stands off the page.
It effectively bakes the ink, causing it to puff up. It achieves a tactile raise at a fraction of the cost of engraving. But there is a severe physical limitation here. While thermography works reasonably well for typography and thin line art, it fails catastrophically if applied to halftones like photographs or large solid blocks of color.
Yeah, that's a mess. Because of the physics of how the powder melts and bubbles under heat, it cannot form a perfectly smooth, flat surface over a large area. If you attempt to thermograph a large corporate logo, the resulting surface will pool, crater, and cure with a deeply pitted, mottled appearance.
It ends up looking like the textured skin of an orange.
Exactly. It completely shatters the illusion of quality. The designers must strictly limit thermography to fine lines and text.
Good tip to keep in mind. Moving away from the antique and the tactile, we have to look at production methods that manipulate optics and alternative materials. If we look at holography, we are dealing with pure light physics. This isn't just a shiny sticker. True holography creates complex three-dimensional imagery on a perfectly flat two-dimensional surface.
It's honestly mind-bending tech. The creation of a holographic master is an exercise in high-end optical engineering. It begins with digitizing imagery and separating it into highly specific depth planes. Then, using highly calibrated lasers bouncing off precise mirrors, those layered images are exposed onto a photosensitive master plate. The interference patterns of the laser light create microscopic grooves.
And then that master plate is used as a die. It is pressed under extreme pressure into a web of coated paper or plastic that has been vacuum metallized. The metallic layer is physically embossed with those microscopic laser-generated grooves.
Right.
When ambient light hits that embossed metallic surface, the grooves diffract the light, recreating the illusion of the distinct 3D layers. This is why your credit cards and shiny trading cards look like that.
Exactly. It is stunning technology, but the supply chain realities are severe. Creating that initial laser-etched master plate requires weeks of lead time and a massive financial investment working with highly specialized vendors. It is entirely cost-prohibitive for a small-run promotional piece. Holography is only deployed when the unit cost can be driven down to pennies through sheer volume.
Like mass-market credit cards, millions of sports trading cards, or anti-counterfeiting security features on global product packaging.
Exactly right.
Now, another optical trick relying on mass production is lenticular printing. This is the classic animated winking eye effect you see on promotional cups or novelty cards. You physically tilt the object and the image completely changes.
Lenticular relies on the precise marriage of specialized printing and extruded plastics. You begin by digitizing 2 or more separate images. Software slices those images into microscopic, alternating linear strips. Strip 1 of image A is printed directly next to strip 1 of image B, and so on. To the naked eye, the printed paper just looks like a heavily blurred, vertically interlaced mess.
But the illusion is activated by the material laminated over it. A sheet of clear plastic is applied perfectly in register over the printed strips. But this plastic isn't flat. The top surface is extruded with dozens of microscopic parallel convex ridges. These are the lenticules or lenses.
Yes, and when those lenses are perfectly aligned with the printed strips beneath them, they act as selective magnifiers. When viewed from a specific angle, the curvature of the lens magnifies only the strips belonging to image A, blocking out image B.
Oh, wow.
Yeah. And as the viewer alters the viewing angle simply by tilting the card, the optical focus of the lens shifts, magnifying only the strips of image B. You achieve physical animation without any digital screens or moving parts. But, much like holography, the required precision interlacing and the cost of the extruded plastic lenses dictate that lenticular printing is strictly a mass production tool.
Now, what if the challenge isn't optical illusions, but the substrate itself? Offset presses require relatively flat, flexible paper. What if a production run requires printing a vibrant, opaque logo on a cylindrical glass bottle, a heavy canvas tote bag, or a sheet of industrial aluminum? We moved into the territory of printing on the unprintable, starting with screen printing.
Screen printing is the ultimate utilitarian process because it is largely agnostic to the physical shape or rigidity of the substrate. The mechanics are highly direct. A stencil, which acts as a negative mask of the design, is photographically or chemically adhered to a screen composed of tightly woven, finely stretched mesh.
The screen is positioned closely above the object, whether that's a flat metal sign or a curved plastic bottle. A thick reservoir of ink is applied to the screen. Then a firm rubber squeegee is drawn across the mesh with significant downward pressure.
Right.
The squeegee physically forces the viscous ink through the microscopic open pores of the stencil and directly onto the substrate below.
And because the mesh can stretch and the pressure is localized, it can conform to unusual shapes and deposit an incredibly thick, opaque layer of ink on virtually any material: fabrics, acrylics, woods, metals. However, the physical reality of forcing liquid through a woven grid creates a severe limitation regarding resolution.
You simply cannot hold ultrafine detail.
Yeah.
If you attempt to screen print a halftone photograph, the dot structure must be incredibly coarse. For context, a high-quality offset art book might utilize a halftone screen ruling of 175 or 200 lines per inch, rendering the dots virtually invisible.
Right.
A screen print, because of the mesh limitations, often requires a coarse ruling of 65 to 85 lines per inch. The individual dots become highly visible, resulting in a stylized, heavily graphic aesthetic, reminiscent of vintage pop art. It is ideal for bold, flat colors and robust typography, not delicate, continuous tones.
Precisely. And if we need to print on highly irregular, unyielding substrates, but at the massive, terrifying speeds of web offset, we turn to flexography. Flexo is the undisputed king of the packaging sector. It operates on continuous webs, but it abandons the delicate, flat, aluminum chemical plates of offset lithography.
Right. Flexography utilizes flexible, raised plates made of soft rubber or photopolymer plastics. It is, functionally, a massive, high-speed rotary rubber stamp. And the reason you must use soft, compressible rubber plates is due to the volatile nature of the materials being printed.
Just imagine attempting to run a thin, incredibly stretchy plastic grocery bag or a deeply textured, bumpy sheet of corrugated shipping cardboard through the unyielding high-pressure steel and aluminum cylinders of an offset press.
It would be a disaster. The cardboard would be crushed, the plastic would tear, and the rigid metal plate could not deposit ink into the deep valleys of the corrugated surface.
Exactly. But a soft, rubber flexographic plate acts as a conforming cushion. It gently kisses the delicate tissue paper without tearing it, or it squishes down into the rough, uneven topography of a cardboard box, ensuring solid ink coverage across the bumps and valleys. Flexography handles the substrates that would literally destroy standard commercial presses.
Okay, so we know how the image gets on the material. But what exactly is the ink made of, and how do we ensure the colors don't bleed into a blurry mess on these machines?
Here's where it gets really interesting.
Because when designing digitally, you simply select a Pantone color and assume it will magically appear. But in physical manufacturing, you're selecting a highly specific chemical function. Let's look at the variations in offset inks. If a designer specifies a high-gloss ink, they are choosing an ink where a significant volume of clear varnish has been formulated directly into the pigment base to provide a built-in sheen.
Right, but that chemical formulation dictates the choice of paper. High-gloss ink is entirely dependent on being printed on a coated, sealed paper stock. If you apply a high-gloss ink to an uncoated, porous paper, the capillary action of the raw wood fibers will simply suck the varnish down into the paper, leaving the pigment stranded on the surface, looking dull and lifeless.
So the gloss effect is entirely neutralized.
Yes. Furthermore, the varnish content means high-gloss inks cannot be used on heat-set web presses. The intense ovens would physically boil the varnish, ruining the finish.
Speaking of those high-speed web presses with the massive inline ovens, they require specialized heat-set inks. The chemistry here is fascinating. The solvents acting as the vehicle for the pigment are engineered with highly specific evaporation points.
Right.
They remain completely stable while on the inking rollers, but the moment the paper hits the high-temperature chamber, those solvents instantly flash vaporize, leaving the solid pigment behind. It's an incredibly aggressive chemical reaction required to keep the web moving at speed without smearing.
And if a design requires a true, reflective metallic finish, we move to metallic inks. These are not merely colored dyes, they are physical suspensions. They contain microscopic flakes of actual metal, aluminum powder for silver colors, and various brass or copper alloys for golds and bronzes, all suspended in a varnish vehicle.
When the ink is deposited, especially on a smooth-coated paper, those microscopic metal flakes align parallel to the surface, creating a continuous reflective metallic sheen. But introducing raw metal dust into ink creates significant vulnerabilities.
Absolutely. Because it is essentially a layer of metal dust sitting in a thin varnish binder, metallic inks have very poor rub resistance. If handled frequently, the metal flakes will physically detach, leaving silver or gold dust on the user's hands.
Was that right, Dale?
Not at all. And more critically, the metal is subject to oxidation. Inks utilizing copper alloys for gold or bronze colors will chemically react with the atmosphere over time. They will tarnish, turning dull, dark, or even developing a greenish patina.
So to mitigate this, Production managers almost always specify a clear, protective overprint varnish to encapsulate and seal the metallic ink away from oxygen and friction.
Exactly. Another highly specialized formulation is fluorescent ink. These inks are blindingly vibrant because they contain complex chemical pigments that do more than just reflect light. They actively absorb invisible ultraviolet light from the environment and instantly re-emit it as visible light. They are literally glowing.
Wow. They offer unparalleled opacity and vibrancy, often used to artificially boost the intensity of standard process color photographs. But the trade-off is extreme chemical instability.
Yeah, that's the warning here. The complex pigments that create the fluorescent effect degrade rapidly when exposed to sustained ultraviolet light. They lack color fastness.
So if a vibrant fluorescent pink concert poster is placed in a sunlit storefront window, the UV radiation from the sun will break down the pigments, fading the piece to a dull pastel in a matter of days.
Exactly. Don't use it for things sitting in the sun. They are fundamentally unsuited for projects requiring long-term environmental durability.
Good to know. Finally, we see a shift in the solvent base of inks for environmental and health reasons, moving from traditional petroleum distillates to vegetable-based inks. By utilizing oils derived from soybeans, linseed, or cottonseed as the primary solvent vehicle, manufacturers drastically reduce the emission of volatile organic compounds, or VOCs.
VOCs are the chemicals that evaporate from petroleum-based inks during the drying process, contributing significantly to atmospheric smog and creating hazardous air quality within the print facility. Vegetable-based inks mitigate this environmental impact while still rendering rich, dense coloration.
Right.
However, their altered chemical profile means they often require adjusted drying times on press, and the specialized formulation can sometimes carry a premium cost.
So we have engineered the perfect chemical ink formulation, but there's a fatal mechanical flaw in attempting to print multiple wet colors onto a sheet of paper moving at terrifying speeds. The paper itself is fundamentally unstable, which brings us to the invisible, highly technical art of trapping tolerances.
Oh, trapping is crucial. Trapping is the concept that separates a digital layout from a press-ready manufacturing file. On a digital monitor, if you design a solid red circle sitting perfectly inside a larger blue square, the mathematical edge of the red pixels precisely abuts the edge of the blue pixels. It is a flawless, mathematically perfect border.
But on a physical press, paper is a living, breathing sponge. As it absorbs the water-based dampening solution, as it is crushed under the extreme pounds per square inch pressure of the impression cylinder, and as it is violently pulled through the machine, the paper physically stretches, warps, and shifts micromillimeters in different directions.
Therefore, if the paper stretches even a fraction of a millimeter between the printing unit laying down the blue ink and the printing unit laying down the red ink, the red circle will not land perfectly inside the blue void. It will land slightly offset.
And because offset inks are inherently translucent, wherever those two colors fail to meet, the raw, glaring white of the unprinted paper will show through. It creates a highly visible, incredibly ugly white gap that instantly destroys the integrity of the design.
The solution to this mechanical chaos is a trap. A trap is an intentional, microscopic digital expansion of the artwork to create an overlapping safety net. Instead of the red and blue touching edge to edge, the Prepress software slightly expands the lighter color, in this case the red circle, so that its perimeter extends a fraction of a millimeter underneath the edge of the darker blue square.
By creating that microscopic overlap, you guarantee that even if the paper stretches or shifts slightly during the press run, the red ink is safely tucked under the blue ink. The white paper is never exposed. The physical mechanics of the printing method dictate exactly how large that overlapping safety net must be. And the required tolerances fluctuate wildly based on the stability of the substrate and the precision of the press, right? Why do the numbers fluctuate so wildly?
It's all about substrate absorbency and press mechanics. Let's look at the gold standard first. Sheet-fed offset printing on high-quality coated paper. The standard trap required is an incredibly minute 0.003 inches, 3/1000ths of an inch.
That minuscule number reflects the immense mechanical control of the sheet-fed vacuum delivery system and the inherent dimensional stability of coated paper. The paper doesn't stretch much, and the press holds it tightly, so the registration is nearly flawless.
Exactly. But if we switch to web offset printing on cheap newsprint, the required trap instantly doubles to 0.006 inches.
Because you are introducing extreme chaos. Newsprint is flimsy, highly porous, and easily distorted. Pulling a continuous web of that weak material through a press under high tension means the paper is stretching and warping significantly between color units. You need a much larger overlap to hide the inevitable mechanical slop.
Right, and it scales up dramatically from there. If you are using flexography to print onto thick, bumpy corrugated cardboard, the trap requirement balloons to 0.010 inches. 10/1000ths of an inch. You are slapping soft rubber plates onto uneven boxes at high speeds. The registration is inherently loose, demanding a massive safety net.
But my absolute favorite metric is for screen printing on textiles and fabric. The required trap is 0.
0, because the material physically traps itself. Fabric is a woven matrix of threads. When you force a heavy deposit of screen printing ink onto fabric, the ink immediately relies on capillary action to bleed and wick outward along the threads. The colors naturally spread and bleed into each other the moment they hit the substrate, automatically eliminating any white gaps. If a designer artificially added a digital overlap on top of that natural bleeding, the colors would severely muddy and look terrible.
Makes total sense. Once you've painstakingly trapped your inks and printed your piece, the ink is sitting there vulnerable to the world. We need to armor it up. It will be shoved into mailboxes, spilled on in restaurants, and scuffed in briefcases. That delicate chemistry needs armor. We need to discuss varnishes, coatings, and physical finishes.
Applying a protective layer is critical for longevity, but the cardinal rule of liquid coatings involves the substrate. Rule of thumb for you listening, these work best on coated papers.
Right. If you apply a clear, protective liquid varnish over a porous, uncoated sheet of paper, the wood fibers will immediately absorb the liquid. It won't cure into a protective shell on the surface. It will sink in unevenly, leaving the paper looking greasy, mottled, and permanently stained. To build a liquid shield, the paper must already be sealed with a clay coating.
Assuming a coated stock, the most basic liquid armor is a spot varnish. A varnish is essentially ink without the pigment. It is applied on the press using a standard printing plate, meaning it can be targeted to highly specific, isolated areas of the design. Costs about the same as another ink.
It is a brilliant tool for manipulating visual contrast. A designer might flood a magazine page with a dull matte varnish to kill the harsh glare of overhead lights on the typography, making the text easier to read. But simultaneously, they can apply a high-gloss spot varnish exclusively over the photographs. The glossy areas catch the light and visually jump off the matte page, mimicking the depth of a traditional photographic print.
It is visually striking, but varnishes offer relatively little physical protection. They will guard against the natural oils in human fingerprints, which is why they are vital over metallic inks, as we discussed, but they will not protect against aggressive scuffing or water damage. For substantial durability, production moves to an aqueous coating.
An aqueous coating is a water-based mixture of synthetic polymers. Unlike a spot varnish, an aqueous coating is generally applied as a flood, blanketing the entire surface of the sheet uniformly at the end of the press run. It costs twice as much as spot varnish, but it cures into a tough, highly scuff-resistant, dirt-resistant, and somewhat water-resistant shell. It is the standard armor for high-quality brochures and presentation folders.
But if a piece is going to face extreme abuse, a heavily handled restaurant menu or the cover of a heavily referenced manual aqueous isn't enough, you must deploy UV coating. This process involves flooding the sheet with a clear liquid acrylic plastic. The sheet is then passed under high-intensity ultraviolet lamps. The UV radiation triggers an instantaneous photochemical reaction, instantly curing the liquid into a completely solid, hard plastic shell.
It provides unparalleled, glass-like gloss and extreme physical durability. But honestly, why not just use this on everything?
Because there is a severe structural penalty for encasing paper in a microscopic layer of hard plastic. If you attempt to take a heavy piece of cover stock sealed in a thick UV coating and fold it in half,
It snaps.
violently. Unlike the flexible paper fibers, the cured UV coating has zero elasticity. When subjected to the sharp geometric stress of a fold, the hard plastic shell cracks, exposing jagged white lines and compromising the integrity of the piece. Designers must engineer folds with extreme caution when utilizing UV coatings. Furthermore, the chemistry of the UV acrylic is highly reactive. It requires the printer to utilize specially formulated wax-free inks, or the plastic coating will simply fail to adhere to the printed areas, peeling off in sheets.
If liquid plastic isn't durable enough, the final escalation in armor is transitioning from liquid coatings to solid laminates, the ultimate shield. Laminating involves taking a physical pre-manufactured sheet of clear plastic film and permanently bonding it to the printed paper using extreme heat and heavy pressure rollers. These films range in thickness from a very thin 0.001 inches to a rigid 0.010 inches.
A laminated piece is practically indestructible in daily use. It can literally be wiped clean with a damp sponge. The physical properties of the armor depend on the plastic polymer chosen. Polypropylene is the most economical laminate. It is relatively soft, meaning it can scuff or scratch if abused, but its flexibility makes it ideal for high-volume applications like book dust jackets.
If you need extreme scratch resistance, you move to polyester film. It provides a much harder, unyielding surface, making it the standard choice for case-bound hardcover books or heavy-duty menus, where longevity justifies the median price point. But the most expensive premium laminate is nylon. And the reason nylon commands a premium is rooted entirely in the volatile physics of paper.
What's fascinating here is that paper retains moisture. Its internal water content constantly fluctuates based on ambient humidity. If you take a large sheet of paper and permanently seal it beneath a rigid, completely impermeable layer of polyester plastic, you trap that moisture inside the wood fibers. As the paper naturally attempts to expand or contract with temperature changes, the impermeable plastic fights it.
The resulting tension causes the entire piece to warp uncontrollably. The cover of a paperback book will curl violently outward, bowing like a potato chip.
Exactly. To prevent this catastrophic curling on lightweight substrates, you must use nylon, because at a microscopic molecular level, nylon film is porous. It breathes. It allows the trapped gases and moisture within the paper fibers to slowly vent and equalize with the atmosphere through the laminate layer. The paper remains stable and flat. It's crucial for paperback covers and metallic inks.
It is brilliant engineering. The highest grade armor is the one with microscopic holes in it. Now, regardless of whether you choose varnish, UV, or laminate, you generally have to choose an aesthetic finish. Glossy or matte? What's the practical advice here?
It is a functional trade-off. Matte or dull finishes diffuse light, offering a highly sophisticated, elegant aesthetic. However, the microscopic texture that scatters the light also readily traps dirt, grease, and scuff marks. A dark matte piece handled by dirty hands will look ruined almost immediately. Glossy finishes, conversely, are highly resilient to dirt, easily wiping clean.
But glossy finishes are absolute magnets for human fingerprints. The oils transfer instantly to the slick surface. However, the most severe production disaster regarding glossy finishes involves the mail system. Crucial warning here.
If you design a stunning, high-gloss, UV-coated postcard intended for a massive direct mail campaign, you must consider how the mailing addresses will be applied. Massive mailing facilities utilize high-speed inkjet heads to rapidly spray the recipient addresses onto the pre-printed cards.
And inkjet ink is primarily water-based. If you fire watery ink at high velocity onto a slick, non-porous, waterproof UV-coated surface, the ink refuses to bite. It instantly beads up, smears across the plastic, and ruins the card.
To salvage the mailing, the facility is forced to print the addresses onto cheap, opaque, white paper adhesive labels and physically slap those ugly stickers directly over the carefully designed, expensive, glossy artwork. It completely destroys the aesthetic intent of the piece. While highly specialized inkjet technology is slowly advancing to fix this, the fundamental rule remains: always verify compatibility with your mailing house before specifying a high-gloss armor on a mailed piece.
Our brilliantly printed, perfectly trapped, and heavily armored sheet of paper is still just a flat sheet. Now it's time for the violence cutting, punching, and crushing it into shape. We move into the sculptor's tools.
The foundational step of finishing is cutting. Earlier, we discussed ganging multiple pieces, say 12 5x7-inch invitations onto a single massive 40-inch press sheet to maximize economic efficiency. Those pieces must now be extracted.
Standard straight-line cuts are called trims. The designer indicates the exact boundaries of the final piece using crop marks, fine lines printed outside the live area in the waist margins. A massive hydraulic guillotine blade, capable of slicing through hundreds of sheets simultaneously with terrifying force, uses those crop marks as a target to trim away the waste paper. Standard trimming is assumed and included in the base cost of manufacturing.
But guillotines can only cut in perfectly straight lines from edge to edge. If a design requires a functional shape, a circular hole in a hotel door hanger, a rounded corner on a premium business card, or a pocket folder cut in the shape of a house, you must utilize die cutting. That's an upcharge.
Die cutting is essentially industrial cookie cutting. To execute it, a specialized manufacturer must physically build a custom tool. They take a thick block of high-density wood and use a laser to burn the complex outline of your design deeply into the board. Then they take ribbons of razor-sharp steel called rules and painstakingly bend, hammer, and wedge them into the laser-cut grooves.
The resulting die board is mounted into a heavy press. The printed sheets are fed in and the die smashes down, the sharp steel rules shearing cleanly through the paper in the exact custom shape. Because creating custom steel dies is expensive, most commercial printers maintain a library of standard, pre-made dies for common items like presentation folders with business card slits, allowing designers to utilize complex shapes without the custom tooling fee.
And there's a highly technical variant of this used in the packaging and decal industry called KISS die cutting.
KISS cutting requires absolute microscopic calibration of the press pressure. It is utilized for adhesive labels, which consist of two distinct layers: the face paper carrying the ink and the adhesive, and the slick, silicone-coated backing paper.
Okay.
The steel die presses down with exactly enough force to shear cleanly through the top layer of paper and the adhesive, but it immediately halts its downward travel. It merely kisses the silicone backing paper without piercing it. This allows the end user to easily peel away the intricate sticker, while the underlying backing remains a structurally sound, continuous sheet.
Brilliant. Moving from cutting to extreme physical manipulation, we have embossing. Earlier, we discussed engraving, which uses ink and immense pressure to create a raised image. Embossing is related, but it is purely structural. It alters the physical topography of the paper without inherently relying on ink.
Embossing utilizes two perfectly mated metal dies, typically sculpted from magnesium, brass, or copper. You have the male die bearing the raised 3D sculpture of the logo or image, and the female die containing the exact corresponding recessed cavity.
The paper is positioned between the two dies. Intense heat is applied, and the heavy press slams the dies together, physically stretching and permanently molding the paper fibers into the three-dimensional shape. If the image is pushed upward, projecting toward the viewer, it is an emboss. If the mechanics are reversed and the image is crushed downward into a sunken valley, it is a deboss.
Right. And if this structural molding is executed on completely blank paper, utilizing only the interplay of highlights and deep shadows across the sculpted fibers to define the image, it is termed a blind emboss. No ink at all. It is an incredibly sophisticated tactile effect. But the physics of the paper heavily dictate the success of the process.
You can't just mold any paper. If you attempt to emboss a lightweight, thin text paper like bond, the aggressive stretching required to fill the cavity of the female die will simply exceed the tensile strength of the thin fibers. The paper will tear and rupture.
Conversely, if you attempt to emboss an ultra-thick, massively rigid cover stock, the paper will refuse to yield. It won't compress into the finer details of the die, resulting in a soft, poorly defined, mushy impression. The ideal substrate is a medium to heavyweight, soft, uncoated cover stock. It has the bulk to fill the die and the flexibility to stretch without tearing. Highly textured papers are particularly dramatic. The immense pressure of the heated dies physically irons the paper fibers completely smooth within the embossed area, creating a striking visual contrast against the rough background.
If a designer wants that embossed logo to not just be raised, but to be an absolutely brilliant, shiny metallic gold, they introduce foil stamping. Foil stamping replaces fluid ink with dry plastic.
A heated metal die presses a microscopically thin carrier film coated with colored or metallic pigment forcefully against the paper. The intense thermal energy melts the pigment layer off the carrier film, permanently fusing it to the paper fibers in the exact shape of the heated die. Over 200 colors are available, and it works on cloth binders and pencils too.
The immense advantage of foil stamping over traditional fluid metallic ink is absolute opacity. Because standard offset inks are translucent, attempting to print a bright yellow ink onto a dark navy blue paper is a disaster. The dark background absorbs the light, turning the yellow into a muddy, illegible green. But hot foil is a solid layer of plastic. You can foil stamp a brilliant pure white or a shimmering gold directly onto pitch black cover stock, and it remains 100% opaque and vibrant.
And when you combine the hot foil process simultaneously with the mated male and female molding dies, you achieve foil embossing. The paper is simultaneously coated in opaque metallic plastic and crushed into a three-dimensional sculpture.
Beautiful. The final aspect of manipulating the paper's physical structure involves folding. And this brings us to scoring, which is a process of creating a crease with a metal wheel.
When dealing with heavy cover stocks or paper heavily coated in brittle ink or UV plastics, a pre-score is mandatory to create a hinge, ensuring the paper folds cleanly without the thick fibers cracking. But the physical execution of folding a scored sheet is deeply counterintuitive to most people.
This was a total mind-blown moment for me reading the text. When the blunt metal scoring wheel presses deeply into the front of the paper, it crushes the fibers, creating a distinct ditch or valley. By displacing that material, it simultaneously forces the paper fibers outward on the back of the sheet, creating a noticeable raised bump or ridge. Now, my natural untrained instinct is to fold the paper into the ditch. I want to hide the ugly ridge on the outside of the fold. But the standard specification dictates the exact opposite. The fold must always be made so that the raised bump, the ridge, is folded onto the inside for minimum stretch.
To understand why hiding the ridge on the inside is structurally necessary, you must visualize the microscopic architecture of a paper fold. Paper is not a single, flat entity. It is a thick matrix of layered wood fibers. When you fold that thick matrix in half, it forms a geometric curve.
And within that curve, the fibers on the outer circumference have a physically longer distance to travel than the fibers on the inner circumference.
Exactly. Because the outer radius is longer, the fibers on the extreme outside of the fold are pulled under immense tension. They are violently stretched. Conversely, the fibers on the inside of the fold are forced into a smaller space. They are subjected to intense compression. When an unscored piece of heavy paper cracks at the spine, it is because the tension on the outer fibers exceeded their elasticity and they violently snapped, fracturing the ink sitting on top of them.
So how does the score line and the position of that ridge solve the physics of the paper stretching to prevent cracked ink?
When the scoring wheel creates the ditch, it deliberately weakens and stretches the fibers on that side. The material displaced forms the raised ridge on the back. That ridge is essentially a localized accumulation of loosened, separated paper fibers.
It's structural slack.
Precisely. If you fold the paper so that the bulky ridge is on the outside of the curve, you are placing the most extreme tension onto fibers that have already been weakened and loosened by the scoring wheel. They will fail and snap instantly. But if you fold the paper so the bulky ridge is on the inside of the curve, that pile of loosened fibers acts as a compressible shock absorber. It provides the physical space and slack needed for the inner radius to crush inward cleanly. By giving the inside of the curve room to compress, you drastically relieve the pulling tension on the smooth, unbroken fibers on the outside of the curve. The outer surface gently bends rather than stretches, and the ink remains intact.
That is absolute microstructural engineering. Placing the bump on the inside relieves the tension on the outside. Rounding out the mechanical tools, we have perforating and drilling. Perforating punches a linear sequence of tiny holes, commonly used for tearing, like reply cards. But binderies also use perforation structurally. If they are folding a massive, thick 16-page signature multiple times, the air trapped inside the folded pages can cause the paper to buckle and wrinkle. By perforating the final fold lines, the trapped air can violently exhaust out of the holes as the paper is crushed flat.
And regarding holes, there is a mechanical distinction between drilling and punching. Drilling utilizes a hollow, high-speed spinning steel bit to bore perfectly round holes through thick stacks of paper simultaneously, primarily for ring binders. The holes are usually 18 to 14 inch. Punching, conversely, uses a solid die to physically smash shapes out of the paper. It is required for the rectangular or complex slots used in spiral or plastic comb bindings, and because of the complex mechanical force required, punching is generally a more expensive operation.
Okay, now that we have all our pieces cut, folded, and perforated, how do we assemble the weird, oversized bits? And more importantly, how do we guarantee we didn't mess up before printing 10,000 of them? We move to the extras and the final check proofing.
Let's start with assembly. The engineering terminology defines how these specialized components integrate into the final publication. We have gatefolds, which are oversized sheets featuring 4 panels. The 2 outer panels fold inward to meet perfectly at the central spine, opening like double doors to reveal a massive panoramic interior spread that dwarfs the standard page size.
If you only need half of that effect, you utilize a throwout. This is a folded sheet that extends outward from only one side of the publication. The critical engineering tolerance here is that the physical width of the throwout panel must be trimmed slightly narrower than the width of the host publication.
Yes. If the fold-out panel were exactly the same width as the magazine page, when you attempted to fold it inward, the edge of the panel would jam directly into the deep crevice of the bound spine. It would buckle, crease, and prevent the magazine from closing flat. It must nest properly.
Other integration methods involve adhesives. A tip-in is an independent specialized page, perhaps a heavy translucent vellum or a fold-out map that is wrapped around the central fold of a signature and permanently glued at the binding edge. A tip-on, however, is a separate, smaller element, like a heavy plastic membership card, a localized coupon, or a product sample that is mechanically pasted anywhere directly onto the surface of a standard host page.
But before the massive web presses spool up to print millions of pages, before the steel dies are hammered, and before the specialized tip-ons are glued in place, the production team must run the gauntlet of proofing. This is the absolute final safety net to catch a disaster early. And the critical strategy here is utilizing multiple highly specific types of proofs. This raises an important question: what exactly are you testing?
Right. You cannot rely on a single proof to verify every aspect of a complex physical object. Different proofing methods serve entirely distinct diagnostic functions. The first and arguably most important physical test involves no printing at all. It's the paper dummy.
The paper dummy is a blank, unprinted prototype. The bindery takes the exact paper stocks specified for the cover and the interior, cuts them to the exact finished dimensions, and binds them together using the specified method. It tests physical reality. First, it allows the designer to evaluate the tactile bulk and rigidity of the object. Second, and critically for massive direct mail campaigns, it verifies the exact physical weight of the finished object for mailing costs. If a catalog pushes the piece just 1/10 of an ounce over a specific postage bracket, that microscopic oversight could trigger hundreds of thousands of dollars in unexpected freight and postage penalties.
Once the physical weight is confirmed, you must verify the chemical interaction of the ink, which is accomplished via an ink drawdown. The ink manufacturer formulates the exact specified color and physically smears a thick layer of it across a 12 by 6 inch strip of the actual specific production paper.
This is absolutely vital when dealing with uncoated or matching corporate colors. Because uncoated paper is highly porous, it absorbs the ink's solvent vehicle deeply, drastically altering the way light reflects off the remaining pigment. A specific Pantone blue will look radically different on an uncoated linen paper compared to a glossy coated sheet. The drawdown physically proves exactly how that specific chemical formulation will react.
We've verified the weight, we've verified the chemistry, and now we need to verify the architectural structure of the layout. Historically and functionally, this is done via a blue line, also known as a Dylux.
The blue line is the structural blueprint of the printing world. In traditional workflows utilizing film negatives, those exact negatives are exposed onto large sheets of photosensitive paper. The chemical reaction yields a monochromatic, entirely blue representation of the entire press sheet. That sheet is then physically folded, trimmed, and stapled into a rough mock-up.
When reviewing a blue line, you're executing a mechanical audit. You are checking text placement, folds, and crossovers. You are ensuring the pages impose correctly. But the crucial limitation is that you cannot be used to check color fidelity. It's entirely blue.
Right. If you need to verify absolute color fidelity in a traditional film workflow, you escalate from a blue line to an analog color proof, utilizing systems historically known as chromalin or color key. These proofs are constructed directly from the high-resolution film negatives. They utilize individual layers of clear polyester film to provide an exceptionally accurate physical simulation, historically the absolute gold standard for color accuracy.
However, the realities of modern manufacturing have largely rendered analog proofs obsolete. The industry has universally shifted toward digital proofs, from laser prints to high-end thermal or inkjet.
And that shift is driven entirely by the evolution of plate making. The vast majority of modern commercial printers no longer utilize physical film negatives. They go direct to plate, where the digital file is beamed directly to a specialized laser that etches the image straight onto the aluminum printing plate. Without film negatives, digital proofs are mandatory.
We have successfully navigated the gauntlet. We have taken flawless digital geometry and translated it into the physical world. We've utilized the chemical repulsion of oil and water to transfer images onto massive rubber cylinders. We've pushed viscous ink through woven silk meshes, and we've melted microscopic plastic toner onto the page. We have engineered the structural slack of a paper fold to prevent outer fiber fracture. We have armored the porous wood fibers and breathable nylon to prevent warping. And we have crushed the substrate under tons of pressure to create tactile topographies.
The overriding reality that any designer or production manager must internalize is that printing and finishing isn't an afterthought. It is a vital, highly technical manufacturing process governed by fluid dynamics, mechanical tension, and organic chemistry. The physical constraints you choose to employ dictate entirely how the final audience will interact with the design.
Which leaves us with a provocative thought regarding the nature of our work today. We spend an immense, almost disproportionate amount of time in modern design workflows agonizing over the digital perfection of our files, the resolution of our screens, the perfect hex codes of our digital colors.
But when you deeply analyze the intense, violent physicality of everything we just explored, the absolute necessity of engineering microscopic digital traps simply to hide the chaotic stretching of wet paper, the ink absorption, the sheer mechanical trauma of a steel die fracturing paper fibers, it forces a reevaluation. Considering all that intense physicality, is a design ever truly finished until it successfully survives the violence of the printing press?
It's an incredible perspective. The digital file is just the theory. The printed object is the proof. Thank you for joining us on this exhaustive, massive journey through the physical reality of manufacturing. If this deep dive helped bridge the gap between your screen and the physical world, please subscribe to the channel so you never miss our breakdowns of complex professional processes. And to explore the absolute depths of these specifications yourself, scan the QR code on your screen or use the link below to acquire the Graphic Design Reference Plus Specification Manual. Until next time, respect the physics of the press. We'll see you on the next deep dive.